Hi everyone, this is Chen from MIT Nanoengineering Group. Today I'm going to present our work on high-performance, flexible thermoelectric generators based on bulk materials. Flexible thermoelectric generators are promising solutions to power supply for wearable devices. However, the high fabrication costs and low output power density of current flexible thermoelectric generators limit their applications. Here, we present a low-cost hairband thermoelectric generators that can power an LED to illuminate a paper for reading in a dark room at 17.5 degrees C without an external heat sink or forced convection at a cold site. Let's get started with a quick intro to the background. Wearable technologies have seen increasing deployment and are fueling the spread of the Internet of Things revolution. Our goal is to build devices powered by human metabolic heat, because most of the time, the human skin has a higher temperature than the ambient, so our body is constantly losing heat to the environment. The average metabolic heat of human body is larger than 5 milliwatts per square centimeter. According to the Carnot's rule, the maximum efficiency is the ratio of the temperature difference between the reservoirs to the hot reservoir temperature. Therefore, we can estimate the maximum output power density of a device operating between the body temperature and ambient temperature to be about 250 microwatt per square centimeter. Given that the power demand of most IoT devices, as you can see examples on the right, is at the order of microwatt to milliwatts, we believe proper utilization of human metabolic heat should be enough to keep those electronics running. On the other hand, thermoelectric generators that convert a temperature difference into electrical energy can provide power to wearable devices and other IoT devices. The dimensionless figure of merit ZT has been widely used to quantify how good the thermoelectric materials are, as we can see from the formula of eta max, the maximum efficiency of heat conversion into electricity by a thermoelectric device. The current commercial materials usually have a maximum ZT around 1 near room temperature. Most past research to enhance the thermoelectric system's performance focused on improving materials figure merit ZT to get a higher energy efficiency. However, the improvement in the overall performance of a wearable thermoelectric system from enhancing the material's properties is relatively limited due to the thermal resistance in other parts of the device can be more significant than the thermal resistance in the thermoelectric materials itself. Though the temperature difference between the skin and the ambient air can be up to 10 to 20 degrees C, the temperature difference across the thermoelectric materials that actually generates power is usually only 1 degree or less if we match the heat flux across the pillars to human skin metabolic heat. The mismatch between the two heat fluxes shown here limit the performance of flexible thermoelectric generators even made of state-of-the-art materials. Another challenge is that the conventional room temperature thermoelectric generators are bismuth telluride-based alloys sandwiched by ceramics, which is not flexible and too bulky for wearable devices. We have been targeting at these two main challenges and making efforts to resolve them. First, to make the device flexible while keeping the desired thermoelectric properties, we choose to distribute discrete commercial bismuth telluride-based alloy pillars in a piece of fabrics. The device is flexible enough that it can be worn as a headband. The cross-section view of one thermoelectric unit is shown here, with the corresponding thermal circuit on the right. The key innovations are the copper electrodes are not only used for electrical connection, but also as heat concentrators and spreaders, and flexibility enabler. The spatial design increased the separation between the hot side and the cold side, so contributing to a larger temperature difference that can generate power. The fabric helps reduce heat leakage and provide comfort for wearing. By tuning the thermoelectric pillar height, air ratio A2 to A1, and the thermal environment parameters, we can obtain their relationship to the output power density, so we can find out the optimum configurations under different circumstances. In this slide, we show the 4-step fabrication process and some tests on wearability. The fabrication process based on our design is straightforward. As sketched out here, the main fabrication steps are: first, the customized bottom copper electrodes with the desired geometry determined by our analytical model are distributed uniformly and soldered together with connecting copper wires. Secondly, the P-type and N-type thermoelectric pillars are soldered onto the bottom electrodes. Next, the thermoelectric units are embedded in a loose knit fabric. And finally, the customized top copper electrodes are soldered onto the thermoelectric pillars, and the connecting wires are soldered to the top electrodes. Given all the material used here are commercially available, and the fabrication steps are rather basic, we believe the scalable fabrication of our low-cost and high-performance flexible thermoelectric generator can be easily achieved. Wearability-wise, the photo here shows how flexible the device is. We have measured the electrical resistance of the device before and after bending. The normalized resistance against bending radius and bending cycles are given in the bottom right. We can see that the resistance of the device stays the same at different bending radii in the range of inches along two directions, AA and BB indicated in the insets, and also after 10,000 times of bending, which indicates the device should be able to sustain more than 10,000 times of wear. To test the device's indoor power generation performance, this photo on the left shows our setup. The wearer is sitting in front of an air chamber with the device on the forehead facing the air outlet. The airflow with tunable temperature and velocity is generated by a fan and sourced from a heating and refrigerated circulator with a heat exchanger. The wind speed and the air temperature at the chamber outlet are measured by an anemometer and a thermocouple placed near the outlet. In indoor testing, the typical power generation as a function of sweeping current of the device, consisting of 50 pairs of P-type and N-type thermoelectric pillars, is given on the right figures. The three curves are at different temperatures, 15, 20, and 25 degrees C. The first one is under little wind condition, and the other is at a wind speed of 2 meters per second. Since the skin temperature varies from person to person, so the power generation performance could change with different wearers. This slide, we show the performance testing results with more volunteer wearers, including female and male wearers, and comparison with our analytical prediction, shown in the dash curves. The skin temperature in the model is set to be 34 degrees C, which is the average hot side temperature we measured. Good agreement is achieved between our analytical model and measurements. Our device measured the maximum output power densities are the highest reported values for flexible thermoelectric generators on human skin without using the external heat sink in similar thermal environments. To give a more intuitive demonstration of our flexible thermoelectric generator's power generation capability, this slide shows that our headband device can power a commercial LED to illuminate a paper for reading in a dark room at around 17 degrees C without an external heatsink or forced convection at the cold side of the device. Hence, we think our flexible thermoelectric generator can be readily integrated with commercial headlamps to light the way for outdoor activities like running, hiking, and camping at night. Moreover, given many IoT sensors require less power than LEDs, since LEDs usually demand a milliwatt level power input, we believe our flexible thermoelectric generator has even more promising IoT applications. In outdoor testing, the headband wearer carries a portable data logger in a backpack, runs outdoor. Like in indoor testing, two thermocouples are attached to a top electrode and a bottom electrode, recording temperatures. The headband is connected to an external resistance of 1 ohm for impedance matching, and the output voltage is being monitored by the data logger. Figures on the right shows our headband with 50 pairs of thermoelectric units can generate a power up to 1.2 milliwatts during an outdoor jog at night at a temperature of 25 degrees C. We notice, despite some fluctuation in the power output curve, the average power curve increases with time due to better heat dissipation at the cold side of the device and potentially increased metabolic heat at the hot side during running. Overall, the output power density aligns with the measured temperature difference between the hot side and the cold side. Besides, we notice in outdoor testing that the fabrics also holds up well against sweat. Finally, please let me highlight the key messages again that we want to share with you. In this work, we adopt the multifunctional copper interconnects that serve as electrodes, flexibility enabler, and heat concentrators and spreaders. The copper spacer design increases the separation between the hot side and cold side of the device, leading to a larger effective temperature difference that actually generates power. The device can be readily integrated into a headband. We use fabrics to provide thermal insulation around the thermoelectric pillars and comforts for wearing. We have demonstrated a flexible thermoelectric generator that achieves the highest reported output power density on human skin. The maximum output power density we measured was 48 microwatt per square centimeter at a wind speed of 2 meters per second and ambient temperature at 15 degrees C. The device is capable to power a commercial LED to illuminate a paper for reading in a dark room at a room temperature of 17.5 degrees C without an external heatsink or forced convection at the cold side. We have also developed an analytical model that can predict a flexible thermoelectric generator's energy harvesting performance under various thermal environment conditions. We believe this work provides a general design approach for high-performance flexible thermoelectric generators at a low cost. The device-level perspectives fill the critical knowledge gap between state-of-the-art material innovations and practical thermoelectric applications. This will conclude my talk today. Thanks for your listening. I'm happy to take questions now.